Hi, Juan. I forgot actually about the pronunciation. Is Juan pronounced good
It's
enough?
perfect. Yeah, it's perfect. Juan, yes. How are you
Juan.
doing? Thanks
Juan.
for the invitation again. It's a pleasure to be
Yeah,
here.
I'm doing actually very good. Still have fun with Java. Lot to do. Yeah.
Adam, before we start, I have a question for you, if I may. What was your first GPU?
Yeah. I had lots of GPUs because back then I was really fascinated by 3D games. I just wanted, to have the perfect graphics. I was not so into gaming. I just liked, the look and feel of the games. And what I remember, so not the game, but I was really excited about Intel MMX multimedia extension.
Okay.
So this one, so I bought Intel with that, and then graphic cards. Okay, so I had the Voodoos. I remember.
Oh, wow. That was the kind of the first ones, right? Before NVIDIA, right? I think.
I think before NVIDIA.
Mm.
Then I think it was ELSA Winner, such a thing. You remember ELSA Winner?
I have no idea.
And they were the 3DFX cards. So this is one of the first cards, but they were not that expensive. So I remember I always bought the graphic cards and the Sound Blaster. You remember Sound Blaster?
Yeah.
Yeah, this was the 3D sound, more or less. But I was not so into gaming. I did some a basic 3D modeling. I was just more excited about the hardware and the PCs. And I also wanted to make it run on Linux. And with the graphic cards were also important for just having a decent resolution on a desktop. Not only for gamings, but you have a really sharp resolution on desktop. Mm-hmm. But since then, I actually ran most of my workloads. Actually, my current server runs without a graphic card, to save to save energy. And since then, nothing. But I think it was ELSA Winner. Then the Voodoo cards. There were cool names actually back then. And I really I forgot to mention. I always create and build PCs by myself. So I could.
Okay. Wow.
I needed the graphic card, so I picked the best one, more or less. So because it didn't matter, I always picked, a good one. Mm-hmm.
Oh, that's great. Okay. I remember my first card it wasn't NVIDIA one, was GT. I believe it's 220, and I bought it during my first job with my first salary, and I bought it to learn.
Your first Ferrari, you said?
No, salary. I wish I could. To learn CUDA actually. That was my first one. And I think my father still uses it because when I left Spain, I left my computer there, and my father took my computer, and my father is still using that one and the same GPU. So it was a good one then.
And I was right. The graphic card was ELSA Winner 1000, and I think S3, and I remember the names 2000 AVI 3D. ELSA is a German company, also created modems, and it was the VESA card. It was local one, and 2012 around, but it should be even earlier. ELSA Winner, exactly. This is what I remember. Trio 64V. I remember the name somehow. And yeah.
Those GPU were programmable. I don't know. But for rendering mainly, I guess.
VESA local bus back then. And they were programmable because I remember my brother, he also created with the OpenGL language a binding for Java and created 3D world.
Oh, wow. Okay. That's
So he was into CUDA programming back then.
And, related to my stuff, yeah.
Yeah, and it worked actually. He created a 3D space actually with that. So it worked.
Mm-hmm. Nice.
Okay. So 1 year ago, over 1 year, it was February when we had the first chat about Tornado. And yeah. And so maybe you introduce briefly Tornado for Java developers. This would be the best part. And then I also have a question and would like to chat, what happened, and maybe alignment.
Yeah, absolutely.
Go ahead.
So Tornado, if I have to, in one sentence, let's say what it is, right? It's a Java parallel framework to accelerate data parallel applications, Java data parallel applications on new hardware. So the use case, the star use case for us is the GPU. So we want to make the GPU programmability as easy as possible from the Java side. Right? But Tornado is not just about a parallel framework. It contains many components, right? Many pieces. It has the API. It has a few compilers in between, to offload from the Java code down to the target code for the GPUs or the FPGAs, etc. And it has a runtime system, and it handles memory for you, etc. So the idea for us is that should be, so for some applications, data parallel applications, we want to make it as easy as possible, right? And make use of the right hardware for your workload. As I say, Tornado, the use case is star use case for GPUs, but it can also run on different hardware like FPGAs, for example, or CPUs, or even now today, these days we're pushing for RISC-V as well, and RISC-V accelerators. Maybe you want to talk about that later. So yeah, you can imagine that as soon as Tornado can target the code we want to accelerate, the framework we want to target for that particular device, for example, OpenCL or CUDA or SPV, then Tornado can make use of that hardware. That's the philosophy. Yeah.
Yeah. And what is Tornado? So I just see that the installation is pretty easy. It gives a TornadoVM installer. And you have a target, a JDK, so something is replaced. I guess this is the...
Right. Yeah. Okay, that's a great question, and I would like to clarify that. So, in reality, Tornado is just a Java program. It's just Java. The only thing it does is the special thing it does is that it compiles Java code as well. But it's just a Java program. So we define Tornado as a plugin to an existing JDK. So we usually run with OpenJDK. We can run with OpenJDK, Mandrel, Corretto, etc., etc. Even GraalVM as well. So essentially, it's just kind of a set of jar files and a shell library to dispatch the native code, and that's all you need.
But are you replacing something in the Java? So
No. The only thing, so Tornado uses, for compilation, uses the Java Virtual Machine Compile Interface. It's called JVMCI. I believe it was introduced, well, I can't recall. I think it was Java 9, but not sure, Java 9 or Java 10, something like that, in JDK. And an implementation of JVMCI is Graal, Git compile. So we use Graal. But we use Graal as a library. We don't we don't modify Graal itself. We extend it to allow for compilation for GPUs or FPGAs and so on.
So you are more like a Graal plugin or Graal?
It could be seen as that, yes.
Okay.
Yeah.
So yeah, Graal extension, you plug into existing JDKs like Graal also does. So I remember back then you could plug Graal to an existing JDK. Back then, now it's more like you download the entire Graal thing, but back then. And from the programming model, I'm on GitHub. And there's two annotations, parallel and reduce, for instance. And if you have a for loop, you can put parallel on it. And then this is like a hint to the compiler that something should happen, right?
That's correct. So Tornado, the APIs have evolved during the past years. We start with annotations, and that's what you see in the first page on GitHub, let's say. And that's the main way we promote to use to developers, right? So Tornado exposes two annotations, two Java annotations, add parallel and add reduce. And those are for hints for the compiler level, right? So we annotate for loops. The user annotates for loops that can be parallelizable. The thing is, the user needs to think about if it can be parallelizable or not, right? It's a bit tricky because we tend to add parallel to everything. Nevertheless, Tornado has some checks. If cannot be parallelizable for whatever reason, we detect the dependencies, Tornado base out to the sequential one. So your code will always be executed, right? Even if it's not on the GPU, it will execute on the CPU as usual. And I think 2-3 years ago, we start thinking another way to express parallelization in Tornado. And we come up with what we call kernel API. And that kernel API is a bit lower level. It's still Java. It's Java objects, etc. But you get used what we call a kernel context. With the kernel context, you can access thread IDs on the GPU. You can access barriers on the GPU. You can access local memory on the GPU. To differentiate, for example, on the GPU, you can program local memory, like L1 cache memory, if you want to. That's pretty common in CUDA and OpenCL. And you can do the same in Tornado, for example. So the thing is, this API requires you to think in parallel. What you express is not a loop for the whole application or the whole program you want to parallelize, but rather the work to be done per thread. And then you launch many threads on the GPU. It could be 100, 1,000, 1 million.
So what should clarify, I think, if you say someone would like to parallelize Java code on the GPU, I think it is mostly mathematical calculations, right? It doesn't make any sense to do something different.
Right, that's a good point. So usually you offload to the GPU heavy compute kernels, usually, right? One key example today, matrix multiply, right? Well, although matrix multiply is also memory bound, but these kind of operations, you do a bunch of floating point operations on a GPU. Yeah, we target like data power applications. We have big data applications. We are running, for example, a project with Gaia project. It's a sub project from the European Space Agency, and they're using. Actually, I think we talked about that last time. They're using Tornado to accelerate some of the kernels, and this is like a DFT physics kernels. DFT style, right? You have a bunch
so usually calculations, right? So
correct.
The developer thinks that you will call HTTP clients. This isn't how GPU is working.
Exactly. What we think is use Tornado for the right tool, right? Tornado has a mode. This is more in the runtime side of things, in which knowing in advance which hardware is best for you is hard, right? Especially if you are not used to run on these devices. So Tornado has a mode that explores that for you in automatic manner. It's what we call it dynamic reconfiguration. So you say to Tornado, I have this code. I want to run it on an accelerator. I'm not saying which one. It's totally abstract. And I'm allowing to Tornado to say, explore with dynamic reconfiguration. It's a call in the API. And what it does internally is compiles and run for all hardware reachable from your workstation, right? For your server or the data center, etc., that you have locally and that node. And then it will give you a metric back. You have some ways to interact with that metric. Usually it's performance. So give me the best in peak performance. So Tornado will run for a while, will evaluate and say, for this one and this data size, the best one is GPU number 1. And the next run automatically switch from the CPU to that GPU, right? Sometimes might happen that says, I know you want to offload, but the best one is still CPU with hotspot. Okay. And Tornado will respect that and continue running with that, right?
So it's like write once, run anywhere on steroids.
That's what we're trying to achieve. Yes, exactly what we're trying to achieve. Yes.
Yeah. So it means if you need data, it means you need numbers. And if you have to perform calculation on the numbers, Tornado and similar frameworks are good for you. Otherwise, it doesn't make any sense to, or GPUs. I mean, then GPUs and similar hardware is good for you for understanding. Otherwise, no numbers, forget about parallelization. Because why I'm saying this, in enterprise project, we have lots of parallelization without any numbers, right? So what we do, we are just calling something externally or database, whatever. This doesn't help, I would say, right? This is completely out of context. Okay, so what we have right now, we have lots of LLMs. Let's say not lots, but we got, for instance, the Llama. We get the DeepSeek from the interesting one, and we get Llama 3 Java. And I know you already look at that. This is the from Alfonso from GraalVM team. Yeah. We covered this on the podcast. I also created a YouTube video to show that it's actually not a trick. It really works. And how this works is you can load all the model weights into memory and perform matrix multiplication basically with SIMD. And it is on my machine. I can have 10 tokens per second roughly. But I never tried with TornadoVM. So have you played with it in Tornado?
Indeed, yes. That's a great question, because I think last time you asked me this, we were starting this project. We have some results now, new things to talk about. So actually, we saw Alfonso's code, and Alfonso, I think he contacted us and said, look, I have this. Well, that was Llama 2, actually. And he said, maybe it's useful to run with Tornado. So we started investigating this, and one of my colleagues started looking into that. And we first tried to port Tornado to run, to accelerate Llama 2. So we did a kind of naive approach. We start thinking, well, is it possible to express this type of operations in Tornado, and how? So we try to accelerate the heavy one. As you mentioned, the matrix multiply is the heavy one. And that should be easy for Tornado. It's it's very easy to express with Tornado, kind of easy to get performance there. Unfortunately, it's not just matrix multiply, it's matrix vector, which is a bit of less granularity, if you like. So we did that, and we evaluate that with, I think, I can't recall, probably it was a 3070 GPU, the NVIDIA GPU. My colleague did this. And we saw a 15% improvement over Java Vector API multi-threaded. That makes sense, right? So it's 15%, it's not that much, right? But that was kind of the first POC for us to kick into this domain. So
it's good that it worked at all, right? This is already the interesting part.
Say again?
That it worked at all. This is the interesting part.
Yeah, exactly.
Because the SIMDs are not GPU bound, so this is the code had nothing to do with, because the Alfonso code was already highly optimized for SIMD. So it's not like it used, for loops Java way. It used, the SIMD operations, which are already optimized for complete different. I would say this is maybe your opponent, right? The SIMD and Tornado are two opposite approaches.
Yeah. Indeed. Okay, you touch the thing. We have to rewrite a little bit the code to get the way we want in Tornado. That's true. So after that,
but for the listeners, for the audience, what it means is, because it was the Llama 3 Java is what I used. And by the way, I was at the DevOps conference. You also attended, I think, one of them. And I showed this on stage, and I got the Llama 3 Java inference on my machine. And maybe 5 attendees asked me, or 1 attendee asked me during the show, and 5 afterwards, whether there's a trick. There's no internet. It really runs. This is Java. How many? There's no DLLs, nothing. It's like no SOs, nothing. They were highly surprised about the performance of Java, and I was able actually to load the entire LLM model to memory. So I think it will be an extremely good use case for Tornado. So if you rewrite this and make it work, I would say this would be a stellar, because this is something everyone can relate to, right?
Yeah. It's not that easy as we thought at the beginning, and I can explain why step by step. I mean, we're working on this very heavily these days. So after that first POC, we start thinking, okay, we want more performance, let's squeeze it. What do we do next? So we saw that the main matrix multiply is basically we have to send data to the GPU to do a few calculations and get data back. So this operation, sending and receiving, in the case of the GPU, goes through, in the case of the discrete GPU, goes through PCI Express. Those operations is low, so you need to take it into account, because you want to compute tokens per second, is the overall end-to-end computation, right? Including data transfers. So I got this idea of having the computation using a shared memory GPU instead, right? So in such a way, transfers are gone, and we do compute.
Like a Mac, right?
For example, yes.
What else? Which other GPUs have that?
Yes, for example, Intel integrated graphics. So the Intel small GPU is inside the CPU and shares the same memory. Yes,
okay.
Actually, that's what the one I target, right? So what I did was to go back to the original version of Llama 2. This is still Llama 2. I get in Llama 3 in a bit. So we got the Llama 2 version, and I rewrote it using the share library that Tornado uses. So a few years ago, we wrote a library for running on integrated graphics using what is called the Intel Level 0 API. This library gives us access to Intel integrated graphics with running with OpenCL or SPV under the hood, right? And it's a very good target to express types with shared memory. So we did that in pure Java, not related to Tornado, but using the same core library, if you like. And evaluate this with integrated graphics and discrete graphics from Intel. We didn't see too much of performance benefits. Well, for Tornado, it might be, but the integrated graphics is not good enough to compete with Java Vector API. And that's the thing.
Wow.
Java Vector API, I was surprised, is extremely good at these things, right? If you have your code vectorized with Vector API, it's surprisingly good. What we saw was the following. In integrated graphics, we can increase the tokens per second by 100 tokens per second, meaning that if Tornado has shared memory in the integrated graphics, we can increase up to 100 tokens per second. Still, it was not enough for this case compared to Java. Still, on the discrete graph.
Why? My machine was 10, I think.
Yeah, but it's Llama 2. I'm running tiny stores.
Okay,
this is not the big. Yeah.
Okay.
Still is the small one. Eh?
Okay.
Yeah. Good point. So we saw that still the discrete GPU was slightly better. As I got to reproduce the same results around 15 to 20% faster. Not enough. So we started investigating a bit more, and we saw recently a repo from, I think it's called, the name is Roger Allen, I believe. He's an NVIDIA data architect. He's an NVIDIA architect. And he had the Llama 2 entirely, the whole transformer in CUDA. So, because we were targeting only one of the kernels in Tornado, not all of it. So then we discussed this internally in the team and said, okay, we can go for it. Let's see what we get. However, getting the whole transformer, we need to expand Tornado, right? So we jumped to Llama 3 then, and then we start analyzing, okay, what do we need? So first of all, we need tensor types, because Llama 3 uses FP8, you know this, right? FP8 and FP16. So we start introducing tensor types for Tornado. This is already done, yeah.
Was it a trigger? What are tensor types in the new Tornado was trigger your evaluation with Llama 3?
We started. Not sure if I got the question. So we jumped to Llama 3 because the code that we looked for CUDA was actually Llama 3 as well, and because we wanted to jump to the Llama 3 also for the Tornado version and using the new Alfonso's code. Yeah. Then we need this FP8, but those are types. We're not using the FP8.
But your proof of concept triggered new features in Tornado.
Correct.
Very cool.
Correct. And I'm getting into this because we have a lot of new features.
Okay.
Now.
Okay.
Boy, it's amazing.
Yeah.
So one of them was tensor types. We have our own representation of tensor types. Hopefully in the future with Valhalla. I don't know if the Babylon will bring. I mean, I wish this could be more standardized, but until then, we have our own representation. And then we need another thing to represent the whole transformer on the GPU. We need to be able to express more complex graphs on the GPU. And maybe I need to roll back how you program in Tornado in general. So before we continue here. So
maybe you roll back even more and explain what a kernel is.
Correct.
Java.
Okay. I was assuming that.
How to write a kernel. If you would write a kernel into Java, how we do this, right? So what the kernel is and how it looks like.
Yeah. So what I call a kernel is a function that will run on accelerator. An accelerator, an example is a GPU, but could be any device. Could be even the CPU. We can deal with the CPU. We can have the CPU as an accelerator. So that's what we call a kernel. In practice, what it means is you want to accelerate a Java method. That's what we call a kernel. I want to accelerate this method. That's my kernel. And that kernel is annotated as we described before with this annotation, a parallel, or you use the other API, the low-level API. You can choose which one. It doesn't matter for Tornado actually.
What is the signature of the function of the kernel?
It's like a normal Java method, nothing special. So the only thing is it has to be for now static. You return void all the time, and the reason for returning void is because the whole method would run in parallel. And if you return something, which thread is returning that? So that's tricky. Okay. Right, so that's why we put void. So you pass the data you want as a parameter, the inputs and outputs as a parameter, but this is Java. It's just Java. It could be a subset of Java.
But it means it has to be almost an array, right? What you're passing.
Exactly. So Tornado has what we call Panama-style arrays. So we already integrated with Panama, and we have float arrays, int arrays, char arrays even, and so on. Tensor arrays. We have 2D matrix types already represented, and so on. So you choose those types for your application.
So you need there's a Java method with at least one array. In this particular case, would be the output array, no input. This would be a valid
that could
kernel.
work, yes. And I can give an example. Monte Carlo is like that. Monte Carlo application. You compute, you have heavy compute in the kernel, and you just want the output of it. Yes.
Okay.
Yeah, that's right. So then what you do is you create a task graph, and that's a key part.
Mm-hmm.
What we call a task graph is a graph that contains many methods. Each task is a method. So you can create a group of tasks that we call a task graph.
Mm-hmm.
And the task graph is just a definition of what you want to offload. Let's say I want method A from class A, method B from class B, and so on. And that's my graph.
Like
so you are not constrained. Sorry?
Like a sequence diagram, right? This
exactly.
method is called, and then the value gets this and this and this. Okay.
Exactly. And also you define your data that you want to pass. For example, matrix A symbol, so I want to copy this data in and out, for example. Mm-hmm. But Tornado doesn't run a task graph, doesn't run anything. It's just a way to, I want this method from this class, this other method from this class, and this data is involved. That's all. Mm-hmm. And then to run it, you create what we call an execution plan. Right? From the execution plan, you pass one or many task graphs, mm-hmm. and the execution plan will compile, analyze, optimize, and run. Essentially, mm-hmm. we do everything for you. So going back to Llama, what we needed to do is to expand this.
The execution plan would be created by Tornado?
The execution plan will be created by the user, by the developer, as well as the task graph. Yes.
Indirectly, right? Because if I have a parallel function, which will call another function, this would be the
Tornado can handle that automatically. It will inline or not, depending on the function.
So it will do this, right?
Yes.
So then I'm creating a task plan without knowing it, right? So I don't have to explicitly create a task plan. It's more like I'm coding in Java, and the task plan is created behind the scenes because Java knows which kernel calls which kernel.
That, I think, could be done. Although we don't do that, we rely on the user to specify the execution plan, because through the execution plan, it's not only running, you can influence runtime behavior. We can get into that.
How this would look like? Let's say I have two methods, right? Two Java mm-hmm. methods. One creates, one fills the arrays, and the other one consumes the arrays and calculates, I don't know, array multiplication, let's say, with 2, multiplied by 2, right? Mm-hmm. So what I have to do with Tornado.
So you have these two methods in a class. Could be the same class, could be different classes. Doesn't matter. As long as it's reachable, is fine. And then you create a task graph, and you say new task graph. You give it a name. A name is a string, and these names are useful if you want to profile or if you want to change the device dynamically, etc. It's very good what you can do there. And then you say the task graph with task 1 is going to be your initialization method, and task 2 is going to be your computation method. That's all, right?
Okay. And this is in Java?
In Java. It's Java. It's just Java.
Good. So it's like DSL. So I can add in...
Indeed, yes. And then you create your execution plan, and you say, I want this execution plan with this task graph that already contains these two tasks in it. Mm-hmm. And then you call execution plan.execute. Mm-hmm. And in that time, Tornado will apply default device, default behavior, default optimizations. But you can influence some of the parameters with the execution plan. You can change the device dynamically. You can call the dynamic reconfiguration we talked about before. You can batch processing automatically. Mm-hmm. You can enable profiler. You can even change compilation flags or change compilation parameters, etc. So it's up to you what to do. Mm-hmm. Mm-hmm. Exactly. So going back to Llama, if I may. Yeah. Okay, great. So what we were missing is the ability to share data across different task graphs in the same execution plan, if that makes sense. So let me rephrase that. We wanted to share some data, for example, on a float array from graph 1 to graph 2 that belongs to the same execution plan, because the execution plan can hold many task graphs, not just one task graph. Mm-hmm. And remember, each task graph can contain many tasks, right? Mm-hmm. So it's kind of building, your building blocks, right? You say more complex and complex and complex. So we want to have the ability to share buffers across different task graphs.
Mm-hmm. Like singleton data buffers, right? Something like this. The shared buffer means multiple kernels could access the same data.
Exactly. Mm-hmm. And that's the key, right?
Okay.
So this also means that we have to be able to run as one of the particular graphs that we want. So you can have your execution plan with 10 different graphs if you want to. And in one particular run, you can say, I want to run 0 and 1 or 2 and 3 and so on. You can pick and choose whatever you want. And that's key because everything in the same execution plan can be shared. Internal data structures, buffers, command queues for OpenCL or streams for CUDA and so on and so forth. So that's a key thing here. Even compilation parts as well. So we did that. So we had the ability now to share data and run the specific graphs. That was the next step. And the last step was...
Question about sharing data.
Yeah, go ahead.
The sharing data, is this a feature of GPUs? I mean, it has to be, right? So what was missing is the API access from Tornado to the accelerators, right?
Okay, sharing data, I want to clarify. So sharing means I create a buffer on the GPU, and the next task wants to reuse that buffer. Right? Because share also could mean, as I was mentioning before, sharing between the CPU and the GPU, which is a bit different concept. Okay.
So on this API was missing. So the create buffer API was missing in Tornado.
Exactly. It was missing the piece of, I want this buffer for this graph, run it for a while, but don't copy back, stay there. So we save the transfer via PCI Express and reuse it for the next set of computation. That's what we have the ability to do now. Right. And that's key to allow to express the transformer in Llama. Plus another missing bit that was not just sharing the buffer, but having the ability to do point arithmetic between different buffers. For example, you want a buffer already on the GPU, like say a matrix, and you want to access a specific row of the matrix within the GPU in different graphs. Now you can do that, right? So all these pieces were missing. And as we speak, I mean, we got this week, we can represent the whole transformer in Tornado. Now we're starting analyzing. I mean, it will take a while because now we're start optimizing things, but the first step, that was the whole transformer in Tornado, is done, which I'm very happy with it.
Which means is magic can happen, right? It means you can express now the entire Llama 3 inference on proper GPU primitives.
That's exactly what we did. Exactly. Yes. Now, it needs to be tuned. We just got it. Now we are tuning it because we have some, issues back, and then, this involves many things. It involves touching the compiler, touching the runtime, touching the GNI code, this dispatch code, and so on and so forth. So yeah.
And on Mac, it could be also interesting because we could possibly switch between SIMD and the GPU, right?
Well, the way you express Tornado is the same. It doesn't matter if it's Mac or not. However, because of the GPU is shared with the shared memory, you can get high bandwidth. So yeah. In fact, we have some examples showing the.
Would be interesting, what's the differences between SIMD and GPU mode? How you call it? Native kernel mode, or how to call the proper GPU access? Accelerated, right?
Accelerator, yes, that's what we call it. Device accelerator, yes. Yeah, and that's where in the point of the Llama code, yeah.
And hopefully soon only Llama? Why prior to that you never had the problem with the buffer?
We didn't have this use case, to be honest, because that's a good point. I think it's important to understand how TornadoVM started and then how it's becoming, right? So TornadoVM started more like a HPC-like, right? Which more closer to what CUDA used to be. Like you run your computation for HPC workloads or data parallel workloads. You have your kernels and you run a specific set of kernels without too many iterations, let's say, between back and forth between CPU and GPU, although you can run iterative algorithms, but it was kind of more static approach what we have. And that's all, right? And then we focus on building the pieces. Like you have to build the compiler, you have to build the optimizer, you have to be careful with data management. All these pieces need to be done. Now was a point that we're getting more use cases, right? I think Llama is the good one because it's not that complex to get there. However, to express it in a way that it makes sense for Java and get performance, I think it's a balance here. So we expand in Tornado with the APIs. I mean, our philosophy is try to keep it as simple as possible all the time. Because there is a point in which if it's not simple enough, probably people will jump to CUDA directly, right?
Yeah.
So instead of doing that, it should be a balance, right? I can give you performance, but keep in mind that if this can be simpler, or if it's simpler, you're losing something else, right? So we're trying to always analyze this balance. With Llama, it's a very good use case because we stress many components of this original system, and we need to expand with these new capabilities. Yeah.
And if Llama is working, then DeepSeek should also work, right? They are mostly compatible.
To be honest, I haven't looked at the DeepSeek code, but if it's kind of Llama style,
yeah, I think it's Llama style.
Probably, yeah. But I have no idea, so don't quote me on this, okay?
Mm-hmm. I have a question, but it is you know what model quantization is, right? It's like you're reducing the size of a model, right? Mm-hmm. I ask myself, I mean, we could do this in Java, right? This would be also a perfect case for Tornado, because what I noticed is the entire quantization happens on Hugging Face. And for me, it is, I don't like it, right? So what I would like to have my own pipeline. I would like to download the model and quantize it and have a smaller model in my pipeline without Hugging Face, because I can download, the Llamas and DeepSeeks directly. Do you know whether it would be easier to do with Tornado?
Well, we haven't looked at that, to be honest. I'm not an expert by any means on this area, so
yeah. But I think what happens is the individual vectors are going to be reduced to save memory, basically. So from a longer, and there are some calculations to be performed. Mm-hmm. So it sounds for me like a perfect use case for another use case, because I don't think there are lots of quantizers in Java, and this is where I'm stunned, because I would actually start with it, right? Because if you have a bag of numbers and you download this, and this is too big, so my first step would be to play with, make it smaller, and then make it usable, right? But it seems like everyone uses Hugging Face quantization.
That's
and,
right.
I'm really interested to implement something in Java, because it's just numbers, and if you have the algorithm, it actually should work. And
Yeah, that's right. So what you're suggesting is to have the actual quantization process accelerated with Tornado. We haven't looked at this yet. It could be the next step for us.
It's really cool. Take a look at this, because
indeed, yes.
Because what you could do then, right? You can have the the origin model, and then quantize it as until it reaches some quality standard. For enterprise, would be interesting, because I make it smaller, now too small, so we pick the last version and it's good enough for us, right?
Yeah, that's a great idea. So I think this fits more like a set of libraries on top of Tornado, if you like.
Yeah.
Right.
Yeah, but they will use Tornado because it's still numbers, and Tornado could decide, okay, I do it on CPU, I don't care, but it will be the same, programming model at least.
Indeed, yes. Mm-hmm. That will be great. I mean, hopefully one day we can reach that point.
And another thing is, are you aware of the DJL library? DJL from AWS, and it is open. If you search for it, it's AWS deep learning framework, and it is fairly popular. And Amazon uses this internally to save money. Actually, this is a parallel Java library. And the interesting part is, what I really like about the entire DJL is, or DLJ, Deep Lava Java,
Deep Java library. Okay, I got it. Okay,
Deep Java library, DJL AI, right? So there's books about it and so forth. And they have an empty method, quantize, but it doesn't work. So I was a little bit sad. But what they have, what you could use, they have an ND array, I think is called. And this looks like Python. So you can say, give me this is the entire API is done. It was really fun to play with. You can say, here's the metrics, fill it and so forth. Maybe you can reuse it because the API is cool. You can say, flip the array, fill it with zeros and whatever, perform matrix multiplication. And this ND array stuff, it is really well done, or it's fun to play with.
Yeah, this reminds me to tensors, perhaps. Not sure which. Conceptually there are differences, but
yeah. What they are doing, this Java API can access TensorFlow and the other libraries. Okay.
Yeah, so Tornado exposes a set of types, tensor types and ND arrays, which is the same concept that we use for.
Okay, maybe so.
Yeah, but as I mentioned, I wish this could be more standardized in the Java side, so all of us can take the same type and perhaps the same interface, and then each one has its own representation. But At least I don't have to rewrite it, or I don't have to explain the user, let's say, use this new API. By the way, there are also new set of types associated with it.
Do you know Mr. I think Zoran Severak is his name?
We have worked with him in the past. Yes.
Yeah, he has deep nets and has vision library, and he standardized the vision part. So there is a JSR, Java specification request in JCP, and I think it speaks nothing against to have standardized a set of API for the arrays, for the tensors in Java, and then everyone would use that. I think it would be even highly appreciated because for me, standards were always great as a developer because I just cared about the APIs, and then never had to relearn them. And I think this could be fun, right?
I believe so. Yes. What I envision is like this kind of new types for modern workloads. I mean, today's the LLM case, but in the future could be anything, right?
Yeah.
Kind of for that domain, that's a set of type that everyone understands, and it's easier for programmers.
Yeah.
Going from different programming language, jumping into Java or the other way around to say, okay, we'll expect this to happen with this type and this type. It's easy for them to reason about, and even less prone to errors, etc. Right? And each vendor can have their own representation or their own optimization, but on top of it, that's.
For instance, the API could be implemented by Tornado and used by UI or Quantizer or whatever, right? So
exactly,
this would be a complete new ecosystem, actually.
I think Babylon. Not sure. I mean, Babylon itself is not jumping into it, but part of Babylon could target that.
This was the next question, but I wanted you to cover all the features. But maybe we cover Babylon right now because you mentioned this already. So the code reflection in Babylon, is this like execution flow, right? You could
how I see it. Maybe we mean different things, but how I see it, code reflection is just in the case of Babylon is for code transformation. It's used for compilation.
But what you get is like AST-like structure.
Yes, in the runtime, yes. Yeah,
this is the meta model, and I think this is part of code reflection. I don't know how it is called properly. And so the code reflection set of annotations where you can annotate stuff, and what you get is like not execution plan, but maybe like a AST for execution plan, right?
Indeed, yes. So I have played a bit with Babylon. Actually, I wrote a blog post some time ago about some differences, more out of curiosity to learn about Babylon because I love these technologies. So I wrote a few examples, and the way it works, at least for this prototype, is you annotate with code reflection, add code reflection, the method you want to offload, and then in HAT, which is a sub-project of Babylon, it's called Heterogeneous Accelerator Toolkit. They provide also an API to interact with this code reflection, with this AST, as you mentioned. And then what they do is to take those ASTs and transform it to lower down from that AST-like down to OpenCL or CUDA PTX or something else, right? So in that that's similar to Tornado in a way. Instead of in the Tornado side, instead of relying on code reflection, we use Graal for that. But the compilation process is very similar, right? We also target OpenCL, we also target PTX, and we also target SPV. So it's kind of very similar.
Could, for instance, Tornado use the AST from Babylon, or are they not compatible?
Well, as it is right now, we can. It's not compatible, but that could be an approach. Remember when you mentioned a very kind of stuck with you, like, the user has to write the execution plan, can be done automatically. Internally we have a lot of discussions about this, and I believe yes, it can be done automatically, and I believe Babylon can help.
Exactly.
Because you can detect the boundaries and you can build your execution plans yourself. The tool can build execution plans for you.
So actually, this would be like the Babylon was higher level programming model where you have a Java code with annotation that creates a structure which is consumed by Tornado.
Exactly. Right? But that's a kind of a different project. I mean, it's cool to have it. Yeah,
I mean, what's the problem, right? The problem is that the LLM inference consumes a lot of energy and is slow. So you need a lot of hardware, even the inference. So if you managed to make it faster and more energy efficient, I mean, it opens everything, right? I mean, if the LLM has to be run on scale and Llama is open source, the next one is Mistral, is highly trusted by European companies because it comes from France. is Mistral or DeepSeek. I mean, it is downloaded, not as bad. It's already analyzed, and you can save money. What you could, because with DJL, this is what Amazon did. So they did it because Python is not multi-threaded, and they could make it with Java, and you will make it even more because you can decide is it CPU or GPU. You could, maybe it's even hybrid, right? I don't know that you have so.
Indeed, yes, yeah.
And a step further, right? So this is not like, I think the future is not like one model. I think the future we get multiple models where like smaller model decides what the next model have to do. And what's also on horizon is like agents. So we have a small application in a loop where we ask constantly what to do, and the LLM decides, and we call basically Java methods. And if you managed, to be faster and more energy efficient than the Python way, I would say, then it opens the door to everything. I mean, then because everyone will be curious, and not curious, this you can save money with Java again, right? So this is what I'm doing in the cloud. Because Java is faster than most other languages, we can save actually in serverless through money, and this is what management would like to see. No, how much can we save, and this is the number. And this is a similar case, right?
Indeed, yes. Well, actually, as you describe it, it looks like easy. It looks very easy, but but it's actually difficult to achieve that. One thing I want to mention. So keep in mind that Tornado offloads Java code. So your kernels are written in pure Java, still Java. Meaning that if tomorrow we don't have GPUs, but we have other type of accelerator, because it's still Java and Tornado has the proper compiler, Tornado still can handle that code on the accelerators, right? Because it's not targeted to a specific platform or specific vendor, etc. Another approach is like using, like a PyTorch is using, for example, which is calling GPU kernels that are already pre-built, pre-compiled, right? Of course, you're going to be very fast. But if you have a new generation of GPUs or you change vendors, you might have to recompile your whole suite of linear algebra functions to run on the new platforms, right? So you don't get that portability there, but you get extremely high performance with that. So Tornado is kind of it's the opposite, right? It's trying to keep in Java as much as possible while offering you as much performance as possible.
Yes, I understood, because the Python PyTorch is more or less fake, only a little happens in Python. And what Python does is cause as soon as possible native code.
The native code, yes. Yeah. Well, I don't really cheat. I mean, it makes sense. If you want to go for performance, you want to product now, it makes perfect sense, right?
Yeah, we could also do that, but your approach is hybrid. But if you take a look at the Llama 2 Inference or 3, so you saw that, the code is maybe 1,500 lines of Java code, everything. So it is actually extremely compact. So the good story is not a lot happens there, right? It's not like we have to write thousands of Java classes. It's more or less like one really long class. And with Tornado, as I said, we could even have a hybrid approach. So this can be, decided where it runs. So it could be multi-threaded, because Java is multi-threaded. We can combine Java multi-threading, even virtual threads in Java. I don't know whether it makes sense in this particular case, with the threading of the GPUs or SIMDs or whatever, right? So we can have multiple levels, or I don't even know whether it's technically possible, but we could address with multiple threads, multiple GPUs, for instance, right? So we could have multiple instances with collaborate, and they access different I/O channels behind the scenes.
Yeah, you touch virtual threads. I haven't experimented with it, but I've been told that virtual threads for just compute might not work well. It's better to use threads like Java threads or streams, for example. In some cases, Java streams are very good.
For computers are not good, but let's say I don't know how many kernels you can start. Let's say 100,000. So every kernel can be represented. Kernel as virtual thread on the outside, so we don't consume, because the virtual thread will only wait until kernel is ready to go, and won't consume any memory or resources on the Java side, just waiting for the kernel. But virtual thread is not very good for compute, right? So because if you would like to do something with the virtual thread, then you need a real thread.
Yeah.
I mean, yeah.
That was clear. One thing I want to mention, so there's another part of work that we have been doing the last year. I mentioned this in a talk that I did, I think a couple of years ago in JVMLS. I had the opportunity to present the status of Tornado until point and our future plans. And at that time, I mentioned that we wanted to work on what we call a Fuse API. Fuse API means, let's get an example. Let's say matrix multiply. As I mentioned, Tornado, what it does is you have your kernel written in Java, and Tornado will offload it to run on the GPU. But the original version was Java. But let's face it. So who writes matrix multiply in Java? I'm pretty sure no one except us, right? So what you want is to use the fastest possible. In fact, what we envision is a mix. You can have some kernels that you want to control yourself, or, or there's no other library that you want to to import for whatever reason, and there are other kernels that you want to call directly, right? So that's what we call Fuse API. So remember, going back to the task graph, you can now design a task graph, and you can say this one is going to be offloaded, and this one is going to be native in cuBLAS, for example, and you can have a mix of them. And for Tornado, it's just another call in the runtime. So yeah, it's very easy. And this is possible now. I mean, we haven't released that yet. We're experimenting, but it is possible now.
I think what will happen is, right? So the obvious use case right now is to run cheap inference of LLMs. So this is like pre-configured thing. I think no one will care what you are doing inside. It only has to work. And what's always, is pain is the entire installation process. And with Llama 3 Java, it is genius because it is one Java file. I don't even have to compile it. I just run Java. It loads the file and I'm done. So, and if I put it, in a CI/CD pipeline where I have to test it, because I run in a cloud with that, it's perfect. I put the model in S3 bucket and I have one Java class and jar and I'm done, right? If you compare it with the Python approach, even, in regulated industry to get everything approved is already problematic a little bit. All the dependencies in Java, we don't have any. This is the cool story. For the Llama 3 Java, there is not a single external dependency. Everything is built in.
Yeah, that's very good. Yeah, that's
this is for compliance. All the highly secure use cases, perfect. And if someone asks, but the LLMs hallucinate, you use such a system. Different use cases like pre-validation of parameters. No one will chat with the LLM. You will hide it somewhere behind a microservice. So this is the first part, and the second part is this is a little bit less common in Java, but we can have a classification workload, so we'll actually train our own models, right? So and now we are talking because then we need primitives and we have to work with scientists because they need, the arrays and they work with the arrays. They need nice UI, and this is completely different use case, right? So this is the Monte Carlo simulation and whatever you said. This is like, complete different beast. But the LLM inference could be also very interesting.
Yes. So we are focusing now in inference, but I mean, the future, we're thinking to also start exploring training. But I think it will get some time to get there. We are heavily focused on the inference part with the whole transformer and the GPU. But that's a really good point. And the fact that you can do, in the fact that you can do everything in Java without any external dependencies, I believe it's great. It proves the platform, right? How powerful it is to write everything you want.
But I mean, this is in let's say more serious project, right? Larger enterprise project or whatever, is always politics in place, security departments and stuff like that. The interesting part, like now in all my projects, in most of my projects, we don't have any external dependencies, which means is there is nothing to maintain, nothing to redeploy if something changes, right? So nothing to document, and this is huge benefit. Huge benefit to other platforms. So I remember in one project we used React, which is normal in JavaScript, but after 2 weeks it was already a security problem there. In Java, there is nothing, and the cool story is if we get one step ahead, and you use the JDK from the cloud provider. So Microsoft built for OpenJDK. or AWS Corretto, Amazon Corretto, then they patch the JDK for you. So it means in our project right now, all the dependencies are managed, by someone else. And with that, this is a huge security benefit, because in worst case, I have one dependency is Tornado. You will patch it for me. I buy support from Tornado Inc. and we are done, right? So I mean, this is how it could be in more serious projects, right?
Well, I wish to get there. Yes, that's a very nice way to put things. Can I ask you a thing? So, are you using LLMs in production now, or kind of pipelines for inference in production?
Almost. So in some project we do experiments, or the LLMs are used because all my larger clients ask me, we need at least the Java LLM story, what we can do. And what they are surprised with is the use cases we introduce with LLMs. Not like we implement an agent, which is I would say not always applicable for enterprise project, because none of the business department people I know so far are willing to have a chat with someone, right? So usually need a form. You still need a key bindings form, copy and paste whatever we had before. It has to run the same way. This is my experience so far. But what we can do, let's imagine in Java, you have an order or a product configuration and complex structure. And this structure can be JSON in Java, right? So it is easy to serialize and deserialize from JSON. So, and you can pass this JSON to LLM and ask, do you see any problems, right? So you can, of course, the prompt is more involved, but at the end of the day, I'm interested, are there any defects or whatever? And this LLM can give you a suggestion. But from this point of view, it is just another microservice. Just another microservice, exactly the same package as all other my applications. They have exactly the same system test. Everything is the same. So what means is it's very appealing, because we can reuse the pipelines, we can reuse the quality standards. Everything remains the same. Nothing.
I see what you mean. Yeah, that's
what
clever.
I mean. So my LLM projects are really boring. We are just accessing via Java interface the LLM and passing the arguments. And if hallucination happens, then if we are lucky, it is outside of the range of the enum. So we exactly know it cannot happen. No.
So essentially, each microservice is a different prompt, but the technology under the hood is kind of the same, right?
Yes.
Right.
Absolutely.
Okay.
Yeah. And we use the Llama 3 Java approach a little bit. There's a Llama as well, and also thinking about Tornado, because we don't need a God model to validate an address, right? So I'm thinking to using smaller and smaller quantized model, right? So I interrupted you again, but this is a too interesting discussion. Now we have to talk more often, then
go ahead,
be more structured. But there is another use case right now which is really appealing. This is called model distillation.
Oh, for image generation.
Yeah, and the model distillation means you have an huge model, and you ask the huge model questions, and you create a smaller model. And the prompts, you have to have a knowledge base, more or less, right? A little bit. So and with this prompts, you can this is how DeepSeek happened. So you can have a smaller model, and I see this also as a business opportunity, because this can happen on TornadoVM entirely. And this is a closed process, and you get your own distilled model, which, for instance, formats the output always in a particular way, stuff like that. And because you have two models on TornadoVM, and they're interacting with each other, and you trade the smaller model, for instance. And for enterprises, they don't like clouds a lot. I mean, most they have clouds, but for such a thing, you can have you can run this on premise. So just saying, there are interesting parts, and I think there are lots of opportunities to optimize. If you have both models on one JVM, maybe you find more optimizations or something like this. Because you can have a use case specific optimizations.
Right, that's interesting. So one project, but that's kind of a separate project I'm working on in Manchester at the university. Is trying to get a better optimization path through LLMs. So basically, Tornado is talking under the hood. You as a user, you don't even notice, with an LLM that is taking, is giving suggestions, which device to use, what are the runtime parameters to use, trying to squeeze a bit more performance, because many things, even for experts, we are not aware of it. And LLMs, if you pass the information, I think can give us a very good hints, right? And in fact, in this use case, if it's wrong, it doesn't matter because you're not losing too much, right?
Exactly.
Unless it's totally wrong, of course, but we're not getting there. Yeah. So yeah, that's another point we just opened a while ago, but yeah, it's kind of interest for us, as you mentioned. So you mentioned distillation. I say image processing. I made a mistake there. So basically, you're kind of inferring new stuff from the original one based on the previous model. That's what you meant.
Yeah. Right? Distillation is this is a common term in LLMs, and this means like instead of fine tuning, this is a more cost intensive. Distillation means you have Llama full, and you create your small Llama with very very narrow knowledge. And this small Llama, this is why it's interesting for enterprises, is better, let's say, in input validation.
But for a specific task, right? For a particular
tasks,
domain,
set of tasks. Okay. You can make it work in a specific domain, and this could run then on Tornado. But then what I will do, right? I will package actually Tornado with the Llama in one single package. And this is my app. This is my microservice. This would be super cool because then I have just one thing to deploy and version. And the model and Tornado, because one thing, there's one microservice called, I don't know, input validator, right? And
yeah, that would be great. I mean, I wish that point in Tornado that we can get there. We're improving still. So keep in mind that Tornado is still an academic project with many things. Although many engineer has been inside.
So less vacations to students, give them some chocolate.
Less vacations for me, I think. Yeah, that's great.
So maybe we cover high level features, and then we schedule if there's more to cover. We can just cover this, but we only mentioned the tensors, right? You implemented the tensors in order to support Llama 3 Java.
Yes. We implement these custom types for representing tensor and FP16, also FP32 as well. I mean, it's just for us, it's just a plain floating point array, let's say, that we use, by the way, internally with Panama APIs, the memory API. And we also have representation for FP16 and FP8. Right? We're thinking maybe in the future to add also FP4. Some of the kernels in CUDA, for example, requires FP4 for higher quantization. But yeah.
In all the Java, I think it was Java 14, there is an half float. Does it help? Does it help you?
We use it. We use it for FP16. Yes.
Okay. Yeah. So it is already helpful.
Yeah. Indeed. Yes. I wish the same for FP8, like a half float, like a quarter float.
Yeah. And you are in touch with the Panama guys?
We have contact with Mauricio, with the main engineer architect in the Panama side. Yes.
Okay. And FP8 is on the horizon, or?
Well, this conversation hasn't come up yet. I mean, probably because we are in contact with the Babylon team time to time. So I think it's good for feedback, not just from us to Babylon, but also Babylon to us, because I think with a lot of synergies can happen there. Especially with the memory API, I love it. We can talk about that later if you want to. But yes, I mean, some of these things had come up, some conversations that come up.
Yeah, the FFM API, you mean?
Exactly, yes. And the FP8 and the need for these quantized types.
Yeah, I even created a short about that because it is really fun to work with. So GNI was not fun at all. But FFM API, what I did for fun, I just called, get hostname. It's a standard C library on Mac. And this was like, the matter of going to the manual page, to the man page, getting the structure, and you just call the thing and you are done. You have the arena, you have to say, is this auto arena, or is it, or you would like to have a confined where you control the arena. And arena is like a scope. And and it's really fun. So I'm thinking now, what else can I call, which is native, right? Back then, I had absolute no interest in calling native code, but with FFM API, it's really fun, I would say.
Yeah. In Tornado, we use the segments. That's how we do now. In the future, we want to transition to pure Panama, including the dispatch of the native code. I mean, we need more people. So,
so if listener of the podcast would like to contribute,
please do contact us. There are a lot of things to do here.
Okay.
Yeah.
So have we covered all the features?
In Tornado? I don't think so.
What some cliffhanger? What else you did and we didn't cover today? We only covered, I think, the tensors and the half flows, right? This is the only thing we covered. And of course, you work on CUDA stuff. The buffer, shared buffer was new. So the shared buffer is a big thing, and this is new, right?
Yes. Well, in Tornado, you can have. I mean, we didn't touch this, but you can have execution plans with multiple tasks that runs on many devices at the same time, even with different backends, which I believe is super cool. It's really cool. So let's say, actually, I did a video. It's in YouTube. I can send you the link, which I explain how to optimize a blur filter application. Blur filter is like an image, okay? That's a JPEG image, that's the input. And we read that image, and the image is actually a plain array, just 3 arrays for red channel, blue channel, and green channel, essentially. And you play with it. And what we want to do is to blur some section of the image, for example. And this is heavy compute. You have it's an stencil style of computation. You have the for loops to traverse the image, and then within these 2 main loops, you have the actual stencil for the tile you want to blur, let's say. And what we do is you have the option to run everything on one GPU, but if you have multiple GPUs, you can split, and each channel will be accelerated on different GPUs. But since Tornado, not only that, because since Tornado is multiple backend, so it has OpenCL backend, CUDA backend, and SPV backend, you can say, I want this task with backend OpenCL, and this other with QTX, and this other with a different backend. In this case, because the task is similar, basically it's the same computation with different data, it would make sense to choose the same GPU. But if you have different tasks with different, granularity or different control flow, you might choose different backends depending on different devices, right? And that can give you an extra speed. In fact, in this video, I show a performance boost of, I think it was 5% boost or 6% boost, just choosing different
this would be also devices. Great for evaluation. What is the best backend, if you have a workload?
Indeed. Because you can select with Tornado the same GPU, let's say, but with different backend. In theory, this should give you the same performance because it's the same GPU anyways. However, coming from OpenCL on the NVIDIA GPU or coming from PTX can give, so there are some differences. First of all, Tornado generates different code-ish. Maybe some optimizations are not enabled on one backend or the other. That's kind of engineering side of things. But also the runtime. So we dispatch the code through the OpenCL runtime rather than the CUDA runtime. And that, depending on the device, can make a difference. We saw that clearly for the Intel side. Running on the Intel integrated graphics through the Level 0 API, it's the new API from Intel, usually give us an extra boost of performance compared to the OpenCL that we run on the same GPU. But
have you any experience with the Intel? I think Gandhi is the name, right? Of the
not yet. We have running on the Arc GPUs. We have a few Arcs around in the lab, but not Gandhi still.
Really interesting to know how good they are, right?
Yeah.
Maybe we should cooperate with Intel. I think Intel is searching for cooperation everywhere, right? Just to be a little.
Well, we worked with them in the past. We have 3-year projects with them. In which we develop an entirely new backend, is this one, the Level 0 with the SPV code for the GPUs. And we are also collaborating right now in another project with Codeplay. Codeplay is an Intel company, and they provide what is called the One API construction kit. So we couple Tornado with the One API construction kit to run on CPUs and get vectorized code on CPUs.
Okay.
And that's quite interesting.
Okay. Can you also have multiple GPUs from one Tornado?
Yes.
So you can have one. So you have one to end to end. So you can have one Tornado, multiple GPUs, and multiple backends per CPU even.
Indeed, exactly.
Per GPU even.
Yeah. Even use the CPU as
well.
So
then the virtual thread should help, because then you maybe get lots of parallel threads. So if you have the image had lots of patches, small patches, and you would like to process every patch in one virtual thread, and there are, let's say, thousands of such threads, then virtual threads would help.
Well, we have an experiment with this. The only caveat I can see is that in that case, we shouldn't use the CPU as an accelerator because already it's consuming the CPU for the Java side of things running the virtual threads, right?
But
and that might slow down the whole.
I think there is nothing to do for the CPU. It's just if you get mounted to the real threads for the if the kernels are done, then you will get the answer now through the platform thread. But if
in that case, yeah. Okay.
If it waits, it does nothing. This is just, I don't think it consumes any CPU, the virtual thread.
Right, in that case might be beneficial. But I haven't tested, to be honest. If someone wants to test it and help us to do this, I'm very happy to hear that. Yes.
Super cool. I would say. Any cliffhanger? What we can talk in the future?
Well, we didn't touch the RISC-V, but we can schedule another meeting
absolutely
for the
RISC-V meeting.
RISC-V meeting. We should make it. We should make it. Yes.
Where people can find you and your project on the internet?
So the project is on GitHub. It's entirely open source. It's TornadoVM. Well, GitHub/Behi Lab is the name of the lab in Manchester /TornadoVM. Otherwise, tornadovm.org. You can find documentation there, videos, and also the links to GitHub. And for myself, I'm mostly active these days on Blue Sky. I can't remember my handle because it's longer. I can send it to you.
Yeah.
Otherwise, put it in the show notes.
Yeah. Perfect. Thank you. And it was fun.
Thank you very much.